Welcome to the Quantum Feedback Loop podcast. I'm your host, James Myers, and I also publish the Quantum Record, which features the latest in science and technology. I sat down with Joe DeMartini, a PhD candidate in astronomy at the University of Maryland, whose studies focus on a type of asteroid known as a rubble pile. Joe is the first recipient of the Schweickart Prize, awarded this June by the B612 Foundation for his innovative proposal to detect and track asteroids during twilight hours. Given NASA's successful 2022 test of technology that could deflect asteroids threatening Earth, Joe's proposal could significantly enhance planetary defense by locating asteroids in the large section of the sky that's difficult for telescopes to observe because of the sun's light. The Schweickart Prize is named after the B612 Foundation's founder, Apollo 9 astronaut Rusty Schweickart, a pioneer who was the first human to walk in space. The pioneering spirit continues, and it was a pleasure to learn from Joe about the new hope that his asteroid detection proposal gives to all of us. Well, welcome, Joe, to the Quantum Feedback Loop podcast. Really excited to have you here today.
Yeah, it's a pleasure to be here. Thanks for having me.
Well, first off, I wanted to congratulate you on being the winner of the B612 Foundation Schweickart Prize for Planetary Defense Against Asteroids. Just for our listeners, the prize is named for Apollo 9 astronaut Rusty Schweickart, who co-founded the B612 and in March 1969 was the first human to walk in space, supported only by his spacesuit. So I'm fascinated to know what it was like for you to meet Rusty and how meeting him has affected your work.
Yeah, I mean, this was kind of a dream come true, right? As an astronomy grad student, somebody who's been interested in astronomy, working in astronomy, you know, the Apollo missions are kind of legendary, especially for those of us in the planetary sciences. And so, you know, you're kind of always sitting there, especially as a young scientist, and you can't help but dream of like, oh man, it would be really cool to get to have a conversation with an Apollo era astronaut, right? Those guys who were some of the first ones out there, you know, up on the moon, some of them, it would be really, really cool. And so, you know, here I was seeing this prize, and you know, it's called the Schweickart Prize, and you see Rusty Schweickart there, and then, you know, moving on to one of the later stages of it, and then suddenly I find out that Rusty Schweickart himself is going to be in the interview stage, and I'm like freaking out, like, oh my gosh, I got to study up. But it was really, really cool. He was very, very knowledgeable, despite not being, as he would say, a numbers guy. Really, really knowledgeable in this visual sense about the dynamics of objects in our solar system in a much different way than I am, having been through this, you know, astronomy and physics grad school program. He's got this really keen visual sense of how things move in space, and it provided a lot of really good insight after I had, you know, been named the winner, about how to sort of tweak things in the proposal to make them make a little bit more sense intuitively for people. He has this knack for simplifying complicated ideas into very easily digestible sound bites that everybody can sort of latch on to. On top of that, he's very philosophical as well, and I think probably partially due to his time in space and the time at which he was in space. It was really inspiring to get to talk to Rusty, and it gave me a really optimistic outlook for the rest of my career, if I can manage to stay in planetary science, planetary defense, which I hope I can.
Well, that's amazing. And, you know, I remember as a very young child watching the moon landing, and it really, yeah, it's something, it's, I guess, a really pioneering thing. We all, I guess, in some sense want to be pioneers. And there he was pioneering the first EVA in space. And then he's pioneering the B612's mission to defend the Earth against asteroids. It's not a mission that receives a lot of press coverage. But in your view, and you know, as somebody who studies objects in space, how important is the planetary mission for defense against asteroids among all of these other priorities that the world has?
So I think the way to think about this is, so in planetary defense, we have this saying that asteroid impacts are the only preventable natural disaster with our current technology, right? There's nothing that we can do to stop an earthquake or a hurricane or tornadoes or anything at this point. But with enough warning, when we know that an asteroid is on a collision course with the Earth, we've just proven with these technology demonstration missions like the DART mission out of NASA's Planetary Defense Coordination Office, that we can deflect an asteroid, we can push it off course so that it won't hit the Earth, right? And so when I think about planetary defense, it's more of a to the average person, right? To the person who's not involved in the space industry in any way, space can be really difficult to grasp, right? It's huge and incomprehensible in many regards. And then the way that you interact with it is in a book or on TV or in a movie or something. And in a lot of these situations, it's, oh my God, here is this killer asteroid coming to destroy the planet. And it can create this sense of fear, right? Which I think stems from that lack of knowledge. And so it's important for those of us who are in the field to have all of that knowledge, because we sort of bear the burden of trust from everybody else that we are experts on this, that we're on top of this, that we're tracking these things, that we have plans in case there's something happening. And so that's really where it is. I mean, these objects are out there. They have hit the Earth before, and they will, probably not in our lifetime, but on the scale of thousands or maybe millions of years. They're out there, they're coming. And if there is a dangerous one, then we need to know that we can do something about it. And it's really reassuring for people to know that the experts at NASA or at all of these other institutions, the European Space Agency, Japanese Space Agency, that there are really, really incredibly smart people who know exactly what they're doing and who have set forth these plans so that we don't have to worry about these. And we can sort of put their minds at ease, let people worry about other things rather than having to worry about buying asteroid insurance or something.
Not that you can insure against such a thing, I guess, but yeah, no, and it's encouraging to know that those other agencies that it's a global effort, right, in this defense. And I guess as we learn more, we can improve more of the technology for both detection, which is, I understand what your proposal is about, but also the technology for actually deflecting the asteroids. And you referred to the DART mission. That was what was it, 2022 mission of NASA, where they sent a probe and managed to land on a space rock and change its trajectory. So that's a pioneering thing.
Yeah, so it wasn't even landing on it. I mean, they shot this satellite up, and basically you have the asteroid system that they went to was the Didymos system. So you have this one asteroid, Didymos, which is sort of a big guy, something like 800 meters in diameter. But Didymos has this little moon going around it, Dimorphos. And so you can use this system as sort of a proxy for an asteroid going around the sun. Instead, you have Dimorphos going around Didymos. And so they just slammed a satellite into Dimorphos to try to change the energy of its orbit. And they managed to change the period, the time that it takes for Dimorphos to go around Didymos by something like 30 minutes, which is really great. It was a cool mission. We got some great images, and there's a lot of really, really great science coming from it now as well.
Yeah, that's really amazing. And you know, I guess as you said, I mean, provided we have enough warning, which is the key, we can mount these missions and improve our ability to mount these missions. But I guess warning is really the key thing, that we need that warning. And so just before we talk about the details of your proposal, how real is this threat in terms of objects circling the Earth? No, we're not circling the Earth, but it could be on a potential trajectory towards Earth. There was, I guess, most recently the 2013 asteroid that hit near Chelyabinsk in Russia. Could have been a real disaster if it hit the middle of the city, but it came with no warning, and there was no ability to defend against it. So, I guess first of all, you know, how real is the threat? And then I'd like to hear about your proposal that won you the Schweickart Prize. Like, how will it enhance our ability to detect asteroids?
Yeah. So you're absolutely right. I was focused on the detection aspect of this. But to answer sort of the question of how real the threat is, the way that we do this is by looking at the past impacts that we know of. And so you're absolutely correct about the Chelyabinsk asteroid, which in 2013 comes down and it sort of explodes over top of this small town in Siberia called Chelyabinsk. And everybody caught it on a bunch of dash cams and things like that. The shock wave from the explosion shattered windows and knocked over some poorly constructed sheds and things like that. In the end, it was approximately $30 million of property damage. And because there's this bright flash first, followed by the shock wave, the sound wave, everybody ran to the windows, and then the glass shatters. And so there were something like 1,500 people sent to the hospital as a result of this. So it really is a big deal, right? Now, the Chelyabinsk asteroid was not big enough to make it down to the ground, thank goodness. But if we look at history, the Chelyabinsk superbolide was something like 20 meters in diameter. 100 years ago, about 1908, in the forest of Tunguska, also in Siberia, there was another large impact, airburst impact event. And you can still see some of the resulting damage to this day in these drone or helicopter images of that area of forest. But there are great images from that time people took of these trees just rayed out from where the center of the blast was. And again, this is not an object that hit the ground. It came close and then exploded in the air. The Tunguska meteorite was also somewhere between 20 and 40 meters in diameter. So if we look at that, one in 1908, one in 2013. There's about 100 years between these things. So we approximate, okay, we'll get a 20-ish meter object every about 100 years. That's a little bit more frequent than we would actually expect based on our collision history models, but there's that. So then we look a little bit bigger. When's the last 100-meter asteroid that we have? I don't have the exact numbers on that, but you look at how big the object is, and a larger impactor is much more rare because they get filtered out by Jupiter, thank goodness, as they're coming in from the asteroid belt. Jupiter's gravity is nice and strong. And they have to go through Jupiter, through Mars, and then somehow make it to the Earth. And so we have this filter of things. We're protected against a lot of the big stuff. But the biggest impact that we know of in Earth's history is the Chicxulub impact, the one that we think killed the dinosaurs. And that was a 10-kilometer size impactor. And so if the Earth is 4.5 billion years old, then we're thinking one of those every several billion years. And then you can sort of scale down from there. We look at the impacts in the moon to try to get information on this because the moon's pretty close to us. And that's how we sort of determine this. But the folks at NASA's Jet Propulsion Lab and the Center for Near Earth Object Studies, and also at ESA's, European Space Agency's Planetary Defense Office, are doing a really good job of finding and tracking these things and determining their orbits. Because once you know how an object is moving in space, very rarely does its orbit change unless there is something really specific that happens to it. If it gets very close to another object, or if it gets reasonably close to a very large object. And that doesn't happen very often because space is mostly empty space, right? And so we look at these objects and we have this database of all of the potentially hazardous asteroids and the risk that they will hit and when they will hit. And none of these, is there any chance of them impacting us in the next 100 years at least? And even then, the chances are minuscule, much worse than your odds of winning the lottery. It's 1 in, I think, 10 billion for even the most dangerous one, and that's decades and decades away. So in terms of how real the threat is, in the near term, not very. But you accumulate those things, and over the long term, like I said, over hundreds, thousands, maybe millions of years, it will happen, right? And we know that it will, and that's why we have to do something to prepare for it. I've just gone and pontificated here for a little while. Can you remind me what the other part of your question was?
Well, I wanted to talk about what your proposal was to deal with these threats. I guess, but just to clarify what you said about the threat level, I guess what you're saying is that the planetary-wide threat level, like the one that hit near Chicxulub in Mexico, is very low, but we still have the threats of, that could threaten a city or threaten a community. And those, as we know from the 2013 event in Chelyabinsk, could be a lot more frequent. I guess it's still an odds game.
Exactly. Yeah. It's absolutely, it's still a numbers game, but you're right. Yeah. The smaller the object is, and where it hits would matter as well. If it hits actually in the water, then it could cause problems all along the coastline. Whereas if it hits over land, then it might be a little bit more contained. Still very dangerous regardless. So that's why we're looking out for them, because we've got to keep an eye on these smaller ones too. Even, regional devastation is devastation, and we don't want any of that.
Yeah. So tell us about your Schweickart Prize proposal. How is your proposal going to enhance our ability to detect these objects that could be potential threats with more advance notice?
Yeah. So I'm glad that you brought up the Chelyabinsk impactor, because this was actually the object that sparked this idea that I had for my proposal. So I want to clarify, I am not an observer. I do models of asteroid surfaces and interiors, but I don't do too much looking at the telescope. And that's not my area of expertise, but I know a lot of really great observers. So I was having a conversation with a good friend of mine, Dr. Carrie Holt. I used to share an office with her before she got her PhD. And we were discussing sort of, planetary defense, and Chelyabinsk had come up. And she said, well, we weren't tracking the Chelyabinsk meteorite that day. We were tracking another asteroid that we thought was going to fly by very close. We didn't know about the Chelyabinsk meteorite until an hour or two before the airburst actually happened. The reason for this was because it was coming from the direction of the sun. And everybody who's ever been to a solar eclipse party or something like that would know that they tell you, don't look at the sun, don't look at the sun, whatever you do, don't look at the sun, because it's very bright and it sort of, for telescopes at least, sort of obfuscates everything else in the sky while it's up there. You can't see stars during the daytime, and that's because of the sun's brightness, right? Well, it's similar for asteroids. Asteroids are really dim objects. I mean, they're just rocks up there. They're not shedding any of their own light. The only heat that they get is from the sun, and that's sort of what we're seeing, or the light reflected from the sun. And so the Chelyabinsk asteroid coming from the direction of the sun sort of points out that there is this population of objects that are difficult to observe, that we're not seeing, that are coming from that sunward direction that could be dangerous to us. If you look at the Atlas system, this is this really cool network of telescopes that are sort of scattered across the world that scan the full sky every night, the full visible sky every night, and look for objects that are asteroids or comets that are close to coming to the Earth. And this is how we track, potential impactors or fireballs or those kinds of things. And they say, they're only covering 60% of the sky because the other 40% is in the direction of the sun. And so I'm sitting here thinking, well, geez, this is this undersampled group. Asteroids don't care what direction they come from when they're coming toward the Earth, right? And so is there anything that we can do about that? And so I continue discussing with my friend Carrie, and she brings up this idea of what are called twilight observations. And this is this really cool thing. So at twilight time, so in the evening, just when the sun has set below the horizon, and in the morning, just before the sun rises above the horizon. So the sun is just below the horizon at either time in the morning or in the night. And you can point your telescope in the direction of the sun because the sun itself is no longer there. Now, the sky is still a little bit bright, but it's darker than it would be otherwise, and you don't have the sun overexposing everything on your telescope. And so we can look in the sunward direction here, depending on the mechanics of your telescope, how low toward the horizon it can point, and search for these near-Earth objects coming from the direction of the sun. I'm going to call them sunward NEOs from now on, if that's okay. And that is the crux of my proposal for the Schweickart Prize. I called it the Sunward NEO Surveillance and Early Twilight Detection Collaboration, or the Sunset Collaboration. You always have to come up with a cute name for these kinds of things.
So in terms of what potentially more we could see if the sun is not obscuring, so finding these NEOs or near-Earth objects, if we were to persist with current methods and not be able to observe this, I think you said 40% of the time the sun is obscuring what we can observe. So if we improve that and we can observe more, like we can observe around the sun, I guess, or avoid the sun in our observations, does that raise our potential to observe to 100%?
So we'll never be able to see 100% of the sky in a given day, right? Because there is always that region of the sky where the sun is. And we're never going to be able to look, exactly when the sun is there. We're also limited by what we call the pointing limit of a telescope. And basically, this is just how far you can tilt your telescope down to the horizontal to look at the horizon. Telescopes are built to look up, or generally in an upward direction. And so really pointing close to the horizon is not something that most of them are built for currently. These twilight observations didn't really start until something like 5 or 6 years ago. And so most of the infrastructure is not constructed for that. But if we do these twilight observations, then we take that 40% of the sky that we don't see in a given night, and we cut it down to maybe 30% or maybe 25%, right? And suddenly we're looking in a region interior to Earth where these other objects might be. It's also not critical to see the entire sky necessarily, because as long as you can see something like 70 or 80% of it, then the rest of what you're filling in are objects that would be inside of Venus's orbit, for example, or objects that are far enough away that we wouldn't be able to see them anyway. So we only need to push in by another, 20 odd percent in order to see most of what we would care about.
Yeah, and improving, if we're talking about an odds game again, improving the odds that we will be able to detect something in time.
Precisely. That is exactly it. The other thing that I should point out here is that everything in the solar system is moving. Everything is orbiting the sun in our solar system. So as the Earth moves around its orbit, we actually have different portions of the sky visible every night. And as these asteroids move around in their orbits, they move into different areas of our view. And so it's this weird, and this is where I was talking about Rusty was really useful, is it's very difficult to visualize exactly how these orbits interact with each other. As astronomers, we have these really cool, mutual motion diagrams, but it can be very hard to visualize otherwise. And so an object is not just sort of moving, or it's not like the Earth is sitting still and an object is moving in a nice clean circle. So if we don't see it this night, we'll see it on the next one. It's the mutual motion of everything that complicates all of this.
Yeah, interesting. And then of course, sunrise and twilight happens at different times all around the planet. So you mentioned the Atlas array of telescopes. Is that primarily what your proposal will use?
So in my proposal, I mostly focused on the upcoming Vera C. Rubin Observatory. This is a really cool, what we call a survey telescope. So Rubin is going to sweep over the sky in a night, the same way that Atlas does. The Atlas telescopes have these 2-meter apertures. So it's a smaller light collecting area than the Rubin Observatory's 8-meter telescope. So a larger telescope, a larger light collecting area means that it can see dimmer objects and it can get a better, what we call signal to noise ratio. That little bit of brightness around in the sky at twilight, for example, would be the background noise. And the signal that we're looking for is the asteroid, which would show up as a couple of pixels generally, right? And so having this bigger telescope and sweeping over large portions of the sky the way survey telescopes do makes it a really, really powerful discovery tool. And that's what we need for these things initially is a discovery tool. What I proposed for the Sunset collaboration was to use the Rubin Observatory, which will get first light next year, I think. So its first observations will begin next year. So I proposed to use the Rubin Observatory for discovery. And then you'll recall I called it a collaboration to use other twilight-capable telescopes to follow up. And the reason for this is a little bit intricate here. So Rubin, as I mentioned, will do these large sweeps of sky. It's got this big aperture, so it's really good for finding things. But you can't just get one observation of something and say, look, I've found an asteroid. Let's put it in the catalog, right? Because then any schmuck with a pair of binoculars can look up at the sky and say, oh yeah, there's one and there's one too, right? I found all these. And we have these really rigorous discovery confirmation requirements from the Minor Planet Center and other bodies. And so what you really need are multiple observations over subsequent nights or a large number of observations in the same night. And so if Rubin is going to be sweeping through the whole sky in a night, and at twilight time, you really only get about 30 minutes to an hour of that time when you can look in the sunward direction. It's not a lot of time, right? If we can find objects with Rubin in a given night and then put out, hey, look, here's this thing. It might be sunward NEO. Any other telescope can then point exactly in that area of space and say, oh, yes, I observed it too. And another one says, oh, yeah, I got 2 observations of it. And another one over here says, oh, yeah, I got an observation as well. And we can compile those with some of these great softwares, like, for example, the B612's Thor algorithm, which I think you did a podcast on late last year. Combine all of these disparate observations and form a high confidence orbit for the asteroid. And then we can confirm a discovery. Now, I'll say, the other beauty of, and I didn't mention this before, but I do want to get it in because I think it's one of the most interesting parts of the proposal here. The reason I propose twilight time is not only because these objects are uniquely observable during that time, but also because it's a time when telescopes aren't doing other science observations. It takes up potentially 0% of other observing time, because generally when it's still a little bit bright out, telescopes don't want to be observing anything. They want to wait for the sky to be nice and dark, and then they get these great images of all of those beautiful images of things that you see on Instagram, right? So it's not using up time when they would be doing other things, and it's a time when we can uniquely observe this population of asteroids that we wouldn't otherwise be able to. And that's why this proposal is sort of unique. And then the collaborative aspect of it is the big thing to improve discovery confirmation. We need to have more than just a single telescope out there. And so that's really what my proposal is. It's the Rubin Observatory, which has plans for its own larger survey, but these twilight observations would take up little, if no, or no extra time. And then following up on what Rubin might discover with any other twilight capable telescope or observatory. And that could even be amateurs.
Interesting, and especially because I understand that there's great competition for time on telescopes. Everybody has projects. Yours is not the only project that people want to use the Rubin telescope for. I think there's a lot of excitement about that upcoming launch of the Rubin telescope. So it's great that yours is not using up resources that could otherwise be deployed elsewhere. That's a really interesting idea for efficiency in that. And so you mentioned the B612 Thor. Maybe if you could just explain a little bit about how that would work with your project, but also maybe other technologies, whether it's machine learning, because obviously, like there could be an infinite number of pixels that you're looking for. So obviously humans are not the sole ones looking at these pixels and comparing them, right?
Yeah, so the Thor algorithm, the really cool thing about the Thor algorithm, and I do a lot of programming in my day-to-day as a PhD student here and a modeler. But so when I was reading about the Thor algorithm, the thing that really stuck out to me that I thought was interesting is that it's heliocentric coordinate system. I'll explain what that means in a second. It's cadence independent and it's observer independent. And those are two really big things. Cadence independence means it doesn't matter when you got the data on the object, as long as you're sure it's the same object. So it could be from 2 nights ago, it could be from 2 weeks ago, it could be from 2 years ago. As long as you've got observations of the same object and you're sure that it's the same object, you can combine those observations. The observer independence means it doesn't matter from where on Earth you observed it. So this is what enables them to combine Rubin observations with dark energy camera observations, with ZTF observations, et cetera, with amateur observations, go on, right? And that's where the Thor algorithm really shines, is its observer independence and its cadence independence. And then it uses this heliocentric system. So rather than a single telescope trying to make its own discovery of an asteroid, knows precisely where it is on the Earth and tracks the asteroid's orbit relative to where it is on the Earth. Instead, it moves everything to the frame of objects moving around the sun. This is what facilitates that observer independence. You no longer care about exactly where you're sitting when you took your observation of it. You've moved to a different frame of reference so that you're just looking in the object's orbit around the sun, heliocentric orbit. No longer with the Ptolemaic model of old. And so the Thor algorithm, what it does is it takes all of these observations and it can combine them to refine an orbit for our object. And this is what I was talking about before. It's finding and confirming to a high degree of confidence an orbit that lets us confirm a discovery, right? So you need to know where it is in space and how fast it's moving. Or you can do our complicated astronomers osculating orbital elements, that's eccentricity of the orbit and how far from the sun on average, and the angle of its orbit, all of these interesting things. But basically position and how fast it's moving is equivalent. And so once you've gotten that down to a really high degree of confidence, we can confirm the discovery and we can say, look, this is an asteroid. It's here, it's moving like this. This is what its orbit will be. We can propagate that once we have it for a few observations and say, look, this is where it'll be for essentially all time until something happens to it. So that's what Thor lets us do in this really powerful way, because no longer do we have to get 4 different, what we call tracklets on, in a time span of 15 days, which would be really hard for twilight observations because we lose 7 degrees of sky behind the sun every night in the western sky every night. And so, this region of sky is moving into that region blocked out by the sun. And so we need to be able to confirm discoveries very quickly. We need rapid discovery confirmation. And that requires, especially for these objects which have a low signal to noise because of the brightness of the background sky, requires an algorithm like this where we can combine disparate observations. Does that answer the question well enough?
That answers the question great. I think it really gave a really good picture, actually, of the sun as this most massive gravitational object in the middle of the solar system. And then tracking everything with relation to that, I guess, makes a lot of sense in that nothing can exceed the sun's gravity. And so, as you say, you're taking out the time and the space of the observation. So the observation is independent of time and space. Yeah, it brings it really clearly to mind, I guess, what the potential of this is, especially with the technology that we have, and whether it's Thor or other computer-based, AI-based applications that can, I guess they're kind of extrapolating from these observations.
Yeah, so if you want to use a machine learning approach or anything like that, for example, it doesn't actually know anything about physics. You have trained it on a bunch of asteroid orbits and observations of things, and then it's kind of making something up to guess where it'll be. And this is fine. It's much more computationally efficient because you don't actually have to do calculations. The computer has come up with, oh, a thing is here, it'll be here, right? And it just takes that step without doing any physics. And it's really, really useful for a lot of instances, but it's not always 100% accurate. You have to make sure that you've trained it appropriately and that there are no biases that you're unaware of. And you have to keep careful track of all of the influences in the model. And that's why a machine learning approach hasn't completely taken off to this point, is because there are a lot of little complications that make it not necessarily easily transferable to this discovery pipeline. And so something like Thor, and I really have to hand it to them, right? I mean, we're talking about this cadence and observer independence, taking the time and space out of it. It's not trivial to do that. The folks doing the development on Thor over at B612 have really done an incredible job. It's really neat to read about the way this algorithm works, and complicated as well, but it's exactly what should be happening. And I think it's the way that makes sense to be looking at things, is it's the way dynamicists, theorists like myself, think about these things. So yeah, so the machine learning stuff, it's definitely usable. I don't think anybody has gotten it quite there yet, though. So it's just out of reach, I would say.
Yeah, interesting. And so how will your proposal affect other planetary defense technologies? Will it have any effect on future DART type missions? Will it have other consequences for planetary defense?
That's not something I've given a great deal of thought to. So the International Asteroid Warning Network, IOWAN, we call it, has sort of set up these 4 stages of planetary defense. They've got searching, detecting, and tracking. That's where I focused. They've got assessing and characterizing, right? That's actually where my research as a PhD student is focused. Then they've got planning and coordination. This is in the event that we know something is going to impact, what are we going to do about it? We coordinate that with disaster response agencies like FEMA, for example, and sort of make a plan for what to do. And then there's mitigation. And this, again, could be the actual disaster response, or it could be like the DART mission, deflection. And so I was really focusing on the searching, detecting, and tracking for this mission. And I moved a little bit into the assessing and characterizing. We're looking with the Rubin Observatory, for example. This is an optical telescope. So we see visible light, the same stuff that humans see with our eyes. And this gives us good information about, for example, the rotation of the object, maybe, or the color of it. There is an upcoming space observatory called NEO Surveyor, which is going to be placed at a stable orbit between the Earth and the Sun. We call it the L1 Lagrange point. Right. So it's this place where it stays in the same place relative to the Earth and Sun's orbits for essentially all time. And this is also going to be able to discover a huge number of these sunward objects and not necessarily sunward objects. NEO Surveyor is going to be a titan for discovery. But it's going to be getting so much of this data. And it also observes in the infrared. And so it's actually complementary with what Rubin will be observing, for example. So if we can observe something with Rubin in the optical and then observe the same object with NEO Surveyor in the infrared, we get size information, color information, and then we can combine that with this rotation information and all of the other stuff we get from the optical. And then we can start to really say something about the interior, the composition, and how dangerous this object might be. So this is what I want the collaboration aspect of Sunset to really be, is we're going to develop this collaboration of follow-up observations, because these big telescopes, these big surveys have their own plans, and they were developed for years and years with their own plans. But they're going to get so much data down that follow-up is going to be difficult. And so if we can establish a dedicated follow-up network, and we can look at these things and say, oh, look, this is something that might be a sunward object. Let's get Sunset's network on it, and then check out this object at twilight time when they're not doing other things, and hopefully make the Earth a little bit safer by detecting and tracking these objects a little bit better. As far as mitigation missions, future planetary defense things, I think really knowing where everything is going to be, knowing which things are dangerous, that's where this helps us. If we wanted to plan another technology demonstration like DART, maybe a sunward object could be viable. Now, it would be difficult to observe, but if we know when it's coming and when it will then be close to Earth, say we pick one that's going to be a close pass, then it would be really, really cool to be able to know that years in advance, and then pick that as a target, and then maybe do the test when it's really close to the Earth, right? Maybe even closer than DART was. That might be interesting. That's as much as I've got for you, though.
Yeah, the collaboration aspect of it, and then the fact that the I1, as you said, is coordinating things or puts things into those categories, so that we need to kind of collaborate with all of those 4 categories that you outlined. And the fact that the NEO surveyor, it's not something that you can put up in the next day, right? It takes years to develop these things. So the more we start the collaboration process now, the more success we'll have during the time that it takes to actually construct and implement these solutions.
And that's precisely it.
So what are the next steps for your proposal?
Yeah, so in the near term, we're looking at supporting and advocating for the Rubin Observatory's twilight microsurvey. So it's not confirmed that the Rubin Observatory will do these twilight observations starting in year 1 of their observing, but Rubin Observatory's the Legacy Survey of Space and Time, LSST, which is interchangeable with the Rubin Observatory here. This is their primary survey. They're widely community supported, and so they want, for these microsurveys that they're saying, they want to know what the community is interested in. And so by Sunset winning the inaugural Schweickart Prize, right, it puts forward this really strong argument that, hey, this is something that people who are invested in planetary defense are really interested in. This is something that we ought to be doing. So that's step 1, is try to get Rubin to be doing these twilight observations. That's looking pretty good. I can't say for certain. I'm not, tightly in the loop on any of this. But it's looking pretty good from what I know. The Twilight Microsurvey was one of their top ranked ones, and it's looking like it might be the only one selected for year 1 as of now.
Amazing.
After that, we want to involve the Atlas network and use them as this sort of final approach discovery and warning tool, right? So we know that Atlas can do twilight observations. There was a study done in 2020 by actually a colleague of mine at the University of Maryland, a research scientist there. And they were able to show that Atlas is capable of observing at twilight. And so if we can get them to do that, then we can take their 60% of the sky and make it 70% of the sky, right? And like you said, when we're playing a numbers game, 10% is a big deal. And so we're just trying to involve more and more. When NEO Surveyor goes up, we involve them as well. But in discussions with some of the folks at the Rubin Observatory, which were facilitated by the connections made thanks to the B612 Foundation, actually, when I received this award, one of the things that was opened up to me was the network that B612 has established and developed and cultivated over years and years. And with that available, suddenly I'm in touch with people who matter at the Rubin Observatory and at Atlas and all other myriad other these big organizations, which is a little bit overwhelming as a graduate student, as an early career scientist who's I'm sitting over here plinking around on my computer all day, and suddenly I'm talking to somebody who makes decisions at Rubin. It's really neat though, and it speaks a lot to how much this prize can help develop and make space for us early career people in this field. But I digress. In my discussions with one of the folks at Rubin, what it really turned out to be was that we need a way to organize which objects need follow-up and which objects are going to be follow-up anyway, Because if Rubin, which is going to be the most powerful thing looking in this space, if Rubin says, oh, we're going to be able to see this object tomorrow night anyway, other people need to know that once they've put the object up as a target of opportunity on the Minor Planet Center database. Not that it's not worth it, but it may not be necessary for the dark energy camera to look at this object if Rubin is already going to be looking at it. And so instead, they can prioritize a different object that may not get another observation. And so establishing this ranking and automated observing software, there's already something that exists like it, but how widely used it is and how easily usable it is, especially by amateurs who there are several amateurs who have made a large number of discoveries. Asteroids are great targets for amateur observers, especially the guys who get really serious about it. And so this ranking system and making it a tool that's easy to use, that might be a really good place to start, or at least to look to try to establish this sunset network, the follow-up network.
And that's really exciting. It's exciting to hear about those networks being built and your ability to connect to them. I'm wondering, now I understand your work primarily to this point was not in planetary defense, and I want to talk about your work, but what's your sense of the range of interest or the amount of interest that scientists are now dedicating to planetary defense? Is that on a noticeable increase? Is it the same as before? Is it?
Yeah, so a lot of the objects that we can go to in the solar system are asteroids. The objects closest to us, aside from the moon, are asteroids, right? It's hard to get to Venus. It's actually hard to get closer to the sun. You need to spend a lot more energy to get closer to the sun than you do to get further from it. That's why we've been to Mars, a dozen times by now, and Venus once or twice. And so asteroids and planetary defense make great mission concepts. And we go to each one and we're surprised every time. There has definitely been an increase in the interest in planetary defense as a result of these recent missions as well. I'll pick out a couple here. The OSIRIS-REx mission recently went, don't ask me what the acronym means, it's a huge one. But it was a mission to the asteroid Bennu, which was number one on the potentially hazardous asteroid chart. It's still, like I mentioned before, no way it's going to hit in the next 100 years. We're 100% certain of it. And visiting the object, there was no perturbation that caused it to move into it. We were very, very careful. I say we like I was on the team. I had nothing to do with it. But we as an astronomers were very, very careful about all of those things before it was even chosen as a target. So OSIRIS-REx goes to the asteroid Bennu, and it goes all around this thing, and it looks at it and has this really interesting top shape, which we think is common for asteroids. It's a C-class asteroid. It's carbonaceous, and we haven't been to a ton of those before. We've mostly been to S-types, stony asteroids, silicaceous. And we find it, we have all these predictions of like, oh, there's going to be like hydrated clays on the surface. And these are from observations that we had gotten before we got there. And, oh, we don't think there will be a lot of boulders. And then we get there and we're like, okay, where are the clays? What's with all of these boulders, And then they do this incredible maneuver. They call it the TAG-SAM, this touch and go sample acquisition mechanism. So the spacecraft slowly descends, and I'm talking like centimeters per second, right? Slowly descends toward the surface of this asteroid and then touches the surface to try to get a sample of it. And instead of touching down on this sand and rock and gravel surface, it pushes straight through. It meets no resistance. And you got to understand, it looks like where they're touching down looks like a pile of sand. It looks like a solid, if you step on sand, maybe your foot depresses a little bit, but you've got support there. They met no resistance, no support. The sampling arm penetrates a half of a meter deep into the asteroid before they fire their gas canister to try to suck up some asteroid material and then launch back away. And so completely surprised by this when it happened. And then we get the DART mission, which was planetary defense specifically focused. And it wasn't a science mission in the same way that OSIRIS-REx was, but it's a technology demonstration. And we tried out things like ion thrusters, and we rammed a satellite into an asteroid's moon to change its orbit. And we got all these great observations. And there's going to be a follow-up from the European Space Agency, the Hera mission. Planetary defense is really cool because, if only because of its name. right? You say planetary defense and it gets the public excited. They think, wait a minute, aliens? And then you say, no, asteroids. And they're like, whoa, asteroids, right? And so with each one of these missions, the excitement around planetary defense absolutely grows. And it's a young field. It wasn't something that we were thinking seriously about until a few decades ago. And the other thing I'll say about it is that I'm in an astronomy department at the University of Maryland as a PhD student there. And a lot of what goes on there is looking at black holes and looking at the stars and the dust between stars and X-ray objects and neutron stars and all of this really, really cool stuff that we can't go to, right? That we can't visit ourselves. And so to have something that we can go to, that we can bring back pieces of and touch and see and do science on is really interesting. And I think it's a good way to show people, to show non-experts that we really are working hard at this, that we're making progress and we're learning more and we're keeping the Earth safer. And that's what builds up that excitement. With each one of these missions, we build it up more and more. The one that I'm looking forward to is the OSIRIS-APEX mission and the recently accepted Ramses mission from the European Space Agency. So I mentioned OSIRIS-REx before. Their spacecraft didn't use up all of its fuel. They've got enough left for this follow-up mission to my favorite asteroid, Apophis. It was discovered in 2004. And when it was discovered, they thought there was about a 2.5% chance of a devastating impact. And 2.5% when it's going to destroy a city is way too big. And so everybody gets on top of this. They start taking more observations. They're looking more closely at this thing. They refine the orbit so much better. And they find out on Friday the 13th of April, 2029, very spooky, I know, Apophis is going to pass between the Earth and the Moon at a distance of just less than 6 Earth radii from our center. So that's inside of geosynchronous satellite distance. It'll be visible to the naked eye over Europe, Africa, and the Atlantic. And it's going to be this incredible opportunity that we've known about for 2 decades to have the Earth's gravity sort of tug and pull on this suspected rubble pile asteroid and stretch it and change the way that it rotates and all of this stuff. It's this natural experiment on an object that is so representative of the class of potentially hazardous asteroids. And so the OSIRIS-APEX mission is going to meet up with Apophis a few weeks after its very close approach. And the Ramses mission is hoping to meet up with Apophis before the close approach and then stay with it through the close approach and do science on it, because the Earth is doing the experiment for us. We don't have to go there and do the touch and go, or like the Hayabusa 2 mission from the Japanese Space Agency, shoot an impactor at their asteroid and see what happens. The Earth is doing the Earth, and the asteroid themselves are doing the experiment for us. All we have to do is be there and do some science on it. And that, I think, is so, so cool.
Yeah, that's fascinating. I didn't realize that there would be that change to the asteroid as it comes between Earth and the Moon, which sounds frighteningly close.
Right.
But it will certainly bring, as you said, the fact that we can observe it with the naked eye. I mean, that would bring, I think, the issue home. And it's only 5 years away, which is
Exactly.
certainly not a long time in cosmic sense or in the perspective of the Earth's own history. So yeah, that's really, really interesting. So just, tell us a little bit about the work that you've been doing primarily. I understand what you're looking at is primarily the composition of these, I think you mentioned rubble piles.
Yeah, so I should define rubble pile for everybody here. I'm sorry. I get excited talking about Apophis and then I really get into it. So a rubble pile asteroid is this sort of agglomeration of individual boulders and rocks and gravel and sand and dust that are held together by self-gravity, right? So every object that has mass has gravity. And we don't experience that attractive gravitational force between me and my cup of water here because it's the Earth's gravity is so much stronger. But out in space, a couple of rocks that are near each other will attract one another. And then, more dust, more debris. The way that asteroids are formed, I'll leave to somebody else to explain. But we get what are called rubble pile objects. And so it's this agglomeration, like I said, of little rocks and dust and fragments held together by their own self-gravity. And so Apophis, we believe, is a suspected rubble pile asteroid. We believe that Bennu, which I was talking about, the target of the OSIRIS-REx mission, is a rubble pile asteroid. We believe that Ryugu, the target of the Hayabusa 2 mission, is a rubble pile asteroid. We believe that Itokawa, the target of the Hayabusa 1 mission, was a rubble pile asteroid, right? It's asteroids in this sort of size range of about 100 meters along their longest axis to about 10 kilometers on their longest axis. And there's nothing certain about that size range. It's all estimates, and it could vary from object to object. But what we don't know is actually what the interior looks like for these rubble piles. So we'll take Bennu for an example. OSIRIS-REx was there for a long, long time. They swept by. They have this incredible map of the surface. They know where every rock and boulder and sand pile is on the surface of Bennu. We don't know what's underneath of that, though. Is it one really big fragment, one really large rock that everything else has sort of accreted to? Or is it a couple of little, large but smaller rocks that are sort of in this some strange configuration? Or is it rubble all the way through, right? Is it, a couple of boulders here, a bunch of sand there, and et cetera, et cetera? We don't know. The only way to know is to drop the seismometer on one of these things, or to use some of these really cool bistatic radar experiments and try to, ground penetrating radar and see what's going on underneath of the surface. What my research actually is I do computer simulations of asteroids. And my only first author publication to this point has actually been about the Apophis Earth encounter in 2029. And so basically what I do is I model rocks or boulders as individual spheres. We model the gravity between those spheres, and we put all of this into the shape of Apophis as best as we know it currently from our observations. And then I throw Apophis by the Earth the way that we think it's going to go, and I see what happens. And what I see when I do that is that across this approximately 400-meter diameter body, I see it stretch just a little bit, right? The Earth stretches it along one axis and compresses along the other two proportionally. And it's by such a minuscule amount, right? We're not going to tear the object apart like we did with Shoemaker-Levy 9 going across Jupiter in the 90s. It's just it's like a breathing, right? The way that you can picture it, it would be on a larger scale, but if you've got like a dodgeball, a rubber ball, and you press it one way and then it sort of expands out the other way, you want to imagine that, but just so much smaller for this asteroid. The scale of millimeters of strain across 300, 400 meters of asteroid, right? But this will create measurable seismic signals inside the body. My simulations indicate that it'll cause cracks and faults that a seismometer on the surface would be able to measure, and that the long period strain of the body through the encounter would also potentially be measurable if your seismometer could get to a low enough frequency here. I've also determined, with the help of a great colleague of mine, Dr. Yeji Kim, that we'll be able to see resurfacing on Apophis as a result of the encounter, right? So you've got these piles of sand or rock or dust and things, and because the Earth's gravity is going to pull stronger on one side of Apophis than on the other, and do that rubber ball stretching, it could cause avalanches on certain areas of the body, particularly dependent on the shape and how highly sloped things are relative to the center of gravity. But we might be able to see some material move downslope and then reveal fresh, unweathered material just below the initially visible surface. And this can be really important in helping us determine where the asteroid came from, what family we say it came from, so where it was in the very early solar system. Can also help us determine, if it's visible, if we've got something there beforehand. I'm really banking on Ramses here. If we've got something there beforehand and we've got something there afterwards, then we can see, okay, what regions actually did resurface and why these regions and not other ones. And those are questions that we can try to predict as modelers, and then I'm really hoping we get surprised when it actually happens, and then there's something interesting to try to investigate.
Incredible, just how much you can learn from just what the rest of us would think of as a piece of rock.
Yes.
But
yeah.
So, and I guess this could assist maybe in planetary defense. I'm imagining, in the sense that the more you know about the composition, the more you know about the potential orbits, as well as the potential consequences of an impact.
So the way that an asteroid rotates can have an influence on its orbital mechanics. There's this really cool effect. We call it YORP. It's a couple of fellows' names for their first initials. Yarkovsky, O'Keefe, Radskiewski, Paddock, right? It's much easier to just say YORP. So we have this cool thing called the YORP effect, where an asteroid is the sun's light sort of heats up the visible surface of the asteroid, and then the asteroid rotates a little bit and then re-radiates. It ejects those photons. And this can increase or decrease an asteroid's rotation. But the Yarkovsky effect, just the first guy's name, over long timescales, this re-radiation of the sun's energy can actually push the asteroid in its orbit a little bit. And when you're talking about, this asteroid coming within the distance of the Earth and the Moon, for a long time, people were worried about, okay, well, what's this Yarkovsky effect? Because over the course of 20 years, it might make a difference in whether Apophis is coming between the Earth and the Moon, and it'll be a really cool natural experiment, or if we need to be worried about this. And Apophis will miss the Earth. I got to repeat this a dozen times. There is Apophis will miss the Earth. It will miss the Earth. Yes, there is. We suspect there is next to no chance that Apophis hits the Earth. And so for us, it is just this really cool experiment. But when Apophis comes by, as I mentioned before, the Earth's gravity will change the way that Apophis rotates. And this could change its orbit in the future. And that's really important to know, right? The way that these things are rotating then affects their orbits. And knowing their orbits to a high degree of precision is important to knowing whether or not we have to deflect this object. The other thing that this natural experiment with Apophis can do for us is give us information about the compositions and potentially the interiors of these S-type objects. So we've mentioned the DART mission a couple of times now, and we don't know what kind of crater the DART mission created on the little moon, Dimorphos. More importantly, before we actually did the experiment, we weren't 100% sure by how much we were going to change the orbit. We were aiming for a few minutes, I think, of period change for the time of Dimorphos going around Didymos. We got 30 minutes, which is much more observable, right? And this is because the ejecta that comes off when you hit this thing, and it shoots off a bunch of dust and little rocks and things, can actually increase the energy of the impact, the energy that you've given to this asteroid or taken away from it. And so that is going to be highly dependent on what the surface is like. If we're going to try to deflect one of these things with a kinetic impactor, we need to know how our impactor is going to interact with the surface. I mentioned that the OSIRIS-REx TAGSAM did not interact with the surface in the way they expected, right? DART may or may not have interacted with the surface in the way we expected. The impact experiment from Hayabusa 2 made a crater in the gravity regime when they were expecting the strength regime, meaning it made a bigger crater than they expected. Again, every time we go to one of these things, we get surprised, man. And so the more we know, the better we can plan in the event that something is going to happen.
Wow, incredibly important work. And I think just as we wind up the discussion here, it's been so fascinating to learn about all of this pioneering work. And really, I guess it ties back again to the kind of pioneering spirit that Rusty Schweickart had in space. And I guess the pioneering spirit that the citizen scientists, you mentioned citizen scientists earlier, are contributing a lot to the detection of asteroids. And so I'm wondering, just maybe in conclusion, what kind of future contributions you think citizen scientists could make, either with your proposal or just for planetary defense in general? How can we contribute in a meaningful way, but also one I think that will inspire people to understand the importance of this? So there was actually a survey, I think it was last year, that said that notwithstanding that planetary defense does not get a lot of press coverage, it is actually one of the top priorities of people surveyed. So what does the ordinary person do next?
If you're somebody who's out there and you've got your telescope, go to these resources on the NASA website. I mentioned before, I'm not an observer, and I'm sorry, I can't tell you exactly what they are, but there are resources out there for you if you're interested in observing something, and particularly asteroids. These are objects that, as a scientist, I am using shape models that are facilitated by citizen scientist observations, occultation data, which is really cool. You sort of can get the outline of an object as it passes in front of a star. It's really easy to go to your local observatory, if you have one, And a lot of them do these observatory nights, and they have talks about from scientists, and then they'll let you look in the telescope. But they also do really cool science. They do observations of asteroids, of planets, of Jupiter's moons. These are things that you can participate in. I mentioned before, there are two citizen scientists, I think, who have made some of the most asteroid discoveries because they have the time to do that. They're doing this on their own time with their own passion. And if you are passionate about it, and if you have the time for it and the drive and the willingness to do a bit of learning as well, then you can make a really, really big difference in the amount of data that we have on these objects. And in that way, in making discoveries and facilitating discoveries, you're helping defend the planet. You're helping with that first aspect of planetary defense that Iwan has laid out: searching, detecting, and tracking. That's something that anybody can be a part of. And I'll tell you, the few times that I've been at an observatory night here at the University of Maryland, we've seen some kids come up to the telescope and have a look at, one of Jupiter's moons or something, and just the awe in their eyes and the expression that they give is incredible. And then to be able to take that and tell them, if you're interested and you want to, you learn a little bit of science, then you can be a part of this without having to do all the work that I've done to try to get my PhD, for example. I've been in school for 10 years now, and that's not necessary, right? You can go out, and there are clubs for citizen observers in most major cities. It's not difficult to get involved if you want to. There's a little bit of knowledge barrier to entry, but NASA really tries hard, and the European Space Agency as well, try really hard to facilitate that for people, because the data that we get as planetary scientists from these amateur observers and these other citizen scientists is incredibly useful and so critical. This increasing the wealth of data for us is massive.
Yeah, and I've seen that passion actually firsthand. The University of Toronto here has annual astronomy nights, and I've seen a whole, like 1,000-person venue full of people just eager to learn about what's out there. So, yeah, I mean, that passion that you just displayed, and the importance of kindling that passion and keeping that going in people, I guess, kind of mirrors the kind of passion that Rusty had in starting the B612 Foundation in this mission of planetary defense. And as you said, it's the only preventable natural disaster. So if there's anything we should have a passion for, it's that.
I 100% agree there.
So listen, Joe, thanks so much for talking to us. It's been so fascinating, and we will definitely want to hear about how your proposal progresses, and we hope that those collaborations come together. So it's been really incredible to hear about all of this, and I just want to thank you for sharing your time with us, and we hope to hear from you soon.
Yeah, thank you so much, James. It's been a real pleasure.
Our thanks go to today's guest, and to you for listening to the Quantum Feedback Loop. Please subscribe to this podcast wherever you get your podcasts, and don't forget to check out The Quantum Record at thequantumrecord.com. The Quantum Record is a monthly journal of philosophy, science, technology, and time, where you'll find the latest developments in our rapidly evolving technological world.